Okay, again, this next video, now this is going to be a short introduction to section 15.2 line integrals, okay? And probably what we'll do is split it up into two parts, this video and a second one. And it has to do with the following concept. Okay, line integrals. All right, so we're going back to integration again, just like we were doing in chapter 14, spent a great deal of time doing it as well. And just as a little bit of motivation about what we're talking about here, gang, let's do this. Consider the following. Okay, so you've got a curve in 3 dimensions, we'll say. Let's suppose that it represents a thin wire, okay? And you want to find the mass of this wire, okay? And let's say whose density is given by the function rho of x, y, and z throughout. Okay, throughout its length s, right? It's a curve, so we use the arc length parameter, the arc length of the letter s. Okay, so the length of the curve is given by this right here. And so at every point along there, again, the density is going to be different. So remember, mass, we have to calculate mass, which is density per times the length, right? So here's the idea. Let's cut it up into tiny differential pieces, which right away, that probably sets in motion things in your mind. You know where this is going, right? I'm going to take a very small differential piece. Okay, say that piece right there, okay? And I'm going to highlight it over here. All right, so I took the entire, so think of taking the entire curve, cut it up into a bunch of differential pieces, right? Infinitesimally small, if you want to use that word, that's fine. So here's one of them right here. Again, the length of that, I'm going to call that ds, okay? The whole curve is s, but this is a differential piece of the curve, so its length is going to be ds. Now, mind you, gang, that thing is really small. You can barely see the daylight between those two little hash marks right there. That's how small this is. So I think we can agree that the density right here over such a tiny, tiny piece of the curve is practically constant. It's not going to vary much. So I think we can say here then that the mass of that element we'll call that dm, and that's going to equal the density times the length, okay? Now you imagine applying that same process all over that curve, okay? The other thing is this, gang, be mindful, like I said, all of these elements are really tiny. That's what allows this to happen. If you think back to your chapter 6, right, where we did all those applications of derivatives, the definite integral rather. Remember, the idea is always the same, right? You start out with something really tiny and then you generalize to the overall picture, the big picture. And so we're not doing anything different right here. All right, so I want to add up all of those elements now, and that'll give me the mass of the entire thin wire. And so therefore, total mass okay, look at the marking now. It's a little bit different than what we've done before, right? So the total mass is given by the sum of all of these elements as they range over the entire curve C. Okay, gang, that's what a line integral is. Okay, we call this a line integral. Let me just say it is rare that you can calculate them as they stand. Typically what we have to do is we have to put those into parametric form. Now we'll see what that means when we start doing calculations, because I want to show you the next video that's after this one, of course. Let me just mention Remember, the differential of the arc length is equal to the speed times the differential of time, right? So this is going to figure prominently in calculating these kinds of line integrals. Now, we can generalize to other scenarios, of course. Not every line integral is going to represent mass. We only did this as a jumping off point, as a little bit of motivation of like why anybody would even care about line integrals, okay? The next one will have to do with vector fields.